Okay, so in this class, uh, once again, thank you for joining this little bit late session. Uh, and my apologies, we couldn't discuss this material in class today. But what I want to talk about is the concept of inverse kinematics. Now, what is inverse kinematics? And in last class, I talked about the concept of inverse kinematics, that is given as given position and orientation of end effector find joint angles or displacement. Now there is an extension of inverse kinematics that is called as inverse dynamics. So that means given forces and torques on end effector, find joint forces and joint moments. So why inverse kinematics is important? So the example I give is, say, 3D printer. So you want to 3D print something. So basically what you want is you want that extruder to go in a certain, from certain position, in certain orientation continuously, so that you can extrude and construct the 3D printed part. So inverse kinematics is probably a very important problem that you will solve as a robotics engineer. And inverse kinematics problem can be solved using the geometry technique, and this can be also solved using analytical technique, and it can be solved using the numerical technique. So in today's class, I will try to give you some ideas and I will work out a simple problem. And in the next class, I will actually work out a slightly complex problem. So the problem that I want to solve today is the same problem that I posed in last class. And that problem is given as this type of problem. So I have a robot arm, and this robot arm has two joints. This is the revolute joint 1. This is the revolute joint 2. And this is a planar problem. So that is actually very simple. So if you want to draw the kinematic diagram is something that we all know. It's something like this. The only thing is this distance and this distance is very close to 0. So this is the robot arm, and I'm gonna give you this distance L1, this distance L2, and this is my end effector. Now, with our convention, this is going to be my base frame. So I'm gonna say X, so Z, and this is Y. So this is going to be my Z naught, X naught, and Y naught. So this is going to be my inertial frame. So if I want to draw my X naught and Y naught, this is going to look like this, X naught and Y naught. Now this problem can be set up in two ways, and I will tell you both the ways this problem can be set up. So I can actually find out the end effector position in the coordinate system X naught and Y naught. So I want to define, and this is very important, and I want you to understand the difference here. I'm going to call this theta 1, and I'm going to call this theta 2. Now, please note theta 1 and theta 2 are both defined with respect to X naught axis, and this is an important distinction. Theta 1 and theta 2 defined with respect to X naught. Now, the alternate representation is also possible. Now, if you look at the kinematic diagram, we always say this is theta 1, and we always say this is theta 2. So I can construct this robot something like this. And there is a subtle difference. So I want you to follow this. So this is theta 1, but theta 2 is defined with respect to, so this is theta 1. So I'm gonna, just for the sake of simplicity, let me show you so that it's easier to visualize. So theta 2 will be defined with respect to the center line or the axis of the first link. And I want you to understand that both these representations are correct. So please note theta 1 defined with respect to X naught, but theta 2 defined with respect to center line of link 1. Everyone understood this? This is a very important distinction, and depending upon how you solve the problem, how you set up the problem, you're gonna get the same answer. But please understand, when we draw the kinematic diagram, our implicit assumption is theta 2 is defined with respect to theta 1. So in other words, the total orientation of link 2, and this is very, very important, and I want you to understand this. The total orientation, this guy, is basically theta 1 plus theta 2. Are you with me so far? I'm looking at the chat window. Please understand that this is super important. So you can solve the forward kinematics by defining A or by defining in B. But all the kinematic diagrams and all the three-dimensional robotics problem that we have worked out so far assumes that theta 2 starts where theta 1 ends. So please note, theta 2 starts when where theta 1 ends. But at the end, you're gonna get the same answer. So first, what I'm gonna do is I'm gonna give you some intuitive understanding of how these problems work out in case A, and then we will talk about how do we work out the problems in case B. So even though, and once again, let me clarify, most of the times our sign convention is going to be B, but for the sake of discussion, I'm going to start with sign convention A, and then we will extend it to sign convention in B. So let me redraw this robot. So this is link 1. This is link 2. This is x0. This is y0. And what I'm going to do is I'm going to define my theta 1 like this, and I'm going to define my theta 2 like this. So the end effector position is L1 cosine theta 1 plus L2 cosine theta 2. Here, this is L1 sine theta 1 L2 sine theta 2. So if I were to draw the position of end effector, I'm going to call the position of end effector is Px, which is the horizontal position, is L1 cosine theta 1 plus L2 cosine theta 2, and my vertical position is Py, which is L1 sine theta 1 plus L2 sine theta 2. Any questions here? So this purely comes from the geometry. Now, let me define the inverse kinematics problem. In inverse kinematics problem, L1 is given, L1 is a link length, L2 is a link length that is known. So L1 and L2 are constant. Px and Py are given. And we need to find, and this is very important, find theta 1 and theta 2. So everyone understood the problem that we are trying to solve? We are given value of px and py, and we have to find out theta 1 and theta 2. So before we start solving the problem for an arbitrary px and py, let me solve the simple problem. So imagine I give you px is equal to L1 plus L2 and py is equal to 0. So px is equal to L1 plus L2 and py is equal to 0. Do you agree with me that I can clearly say that my theta 1 is equal to 0, my theta 2 is equal to 0? Are you with me so far? Everyone understood? If I give you px is equal to L1 plus L2 and I give you py is equal to 0, my theta 1 and theta 2 are going to be zeros. Let me give you another case, and probably you guessed it. If my px is 0, if my px is 0, but my py is equal to L1 plus L2, I can say my theta 1 is equal to 90 degrees and my theta 2 is equal to 90 degrees. Are you with me so far? So these are two extreme cases that are possible, for which inverse kinematic solution is very simple. Now, what I want to do is I want to ask you this question. And this is the same question I tried to pose in the last class. Ideally speaking, I have two equations and I have two unknowns. So the equations are equation 1, equation 2. Unknowns are theta 1 and theta 2. The question is how to solve. So can we add and subtract and try to find out the solution? Can we somehow add these or subtract these and try to get the answers? And unfortunately, if you try to solve this with algebraic technique, means add equation 1, so you cannot add equation 1 plus equation 2, or you cannot subtract 1 minus 2 and then do mathematical jugglery here. That will not give you a satisfactory answer. But one thing that we know, and these relations I want you to remember, is sine square theta plus cosine square theta is equal to 1. So we know for the fact that sine square theta plus cosine square theta is equal to 1. The second trig identity that is going to be super useful is cosine theta 1 is equal to 1 minus tan square theta 1 by 2, 1 plus tan square theta 1 by 2. So and then the second point is sine theta 1 is equal to 2 tan theta 1 by 2 divided by 1 plus tan square theta 1 by 2. So as you know, these are called half angle formulae. So what we can do, so if you square and back substitute, you will realize that it may actually be more complicated. So let's do this. Let me work out this problem. So what I'm gonna do is I'm gonna rewrite the equation something like this. L1 cosine theta 1 is equal to px minus L2 cosine theta 2, and then I'm gonna look at the second equation. L1 sine theta 1 is equal to py minus L2 sine theta 2. So equation 1 and equation 2 are represented something like this. So this becomes my equation 3, and this becomes my equation 4. Now what I'm going to do is I'm going to square equation 3 and add to equation 4. So here is what happens. L1 square cosine theta 1 square plus L1 square sine theta 1 square, and I have here px minus L2 cosine theta 2 square plus py minus L2 sine theta 2 square. Now believe it or not, this made my life a little bit less complicated, because now I have cosine square theta, sine square theta, and I have this big equation on the right hand side, but this guy is 1. So now I'm going to expand the right hand side, and this right hand side is going to look like px square minus 2 px L2 cosine theta 2 plus L2 square cosine theta 2 square plus py square minus 2 py L2 sine theta 2 plus L2 square sine theta 2 square. Now some observations. L1 square is known, px square is known, px is known, L2 is known. Now I want you to observe, we have L2 square cosine square theta, L2 square sine square theta. So these can be combined. So this guy is known, this guy is known, this guy is known. So now my equation actually is simplified px square plus py square plus L2 square, and because cosine square theta 1 theta 2 cosine square cosine theta 2 square plus sine theta 2 square, this guy becomes 1. But the problem is I have these two equations, and I will write these down here. So they become minus 2 px L2 cosine theta 2 minus 2 py L2 sine theta 2. So Again, I just want to clarify and please pay attention. L1 square is constant, that is known. This entire term is known. In this term is known. So please understand the last term here is also known. So this equation, and I just want to clarify, this equation is of the form. So this equation is of the form C is equal to A cosine theta 1, or C is equal to A cosine theta 1 plus B sine theta 1. And in this particular case, this equation is actually theta in terms of theta 2, but I want you to note that this equation is of the standard form that is given over here. This is called as the standard form. Now, here is something that I want to talk about. So imagine a case, and I want you to just imagine in this particular case that L1 square is equal to, just imagine, px square plus py square plus L2 square. Assume that this is possible. Then do you agree with me? If this is true, my C is going to be 0, and I'm going to have an equation A cosine theta 1 plus B sine theta 1. Do you agree with me? Assume one case, there are two cases possible. One case, which is C is 0 and C is non-zero. And it doesn't matter whether A and B, they are positive, negative, or 0. So A could be a positive number, or A could be a negative number, B could be a positive number, B could be a negative number. It really doesn't matter. But at this point, I just want you to understand that standard form can take two possible cases. There are two cases possible in standard form. Either C is 0 or C is non-zero. Everyone understood this? So how do we solve when C is equal to 0? So case 1, C is equal to 0. And in that case, your equation becomes 0 is equal to A cosine theta 1 plus B sine theta 1. So the easiest way to solve this problem, and you probably guessed it, say it is minus A cosine theta 1 is equal to B sine theta 1, and then actually you have minus A divided by B is equal to tan theta 1, and you find the tan inverse. But please note, tan inverse does not tell you the angles in all four quadrants. So tan inverse is only valid in the first quadrant. So if you were to take, and you can try this, if you say theta 1 is equal to tan inverse of minus A by B, the answer that you are going to get is the answer in the first quadrant. But your true angle could be anywhere. So for that, you will use the function A tan 2 or arc tan. So MATLAB function, or you can use arc tan. And arc tan function will give you the tan angle in all four quadrants. But here is another problem. So what if you want to find multiple solutions? So this is what I recommend. So this is my recommended approach. So what I do is, so I write this equation something like this: minus a cosine theta 1 is equal to b sine theta 1. And what I do is I square both sides. So what happens is this becomes a square cosine square theta 1 is equal to b square sine square theta 1. Now, as you know, cosine square theta is equal to 1 minus sine square theta. So this becomes 1 minus sine square theta 1 is equal to b square sine square theta 1. Now, here this equation becomes a square minus a square sine square theta 1 is equal to b square sine square theta 1. And this equation now can be solved to find the values of sine. So, and you can actually follow this through, and then you can find out the values of uh, a square, and actually you can actually find out the values of sine. And the issue here, the advantage here is, since you are trying to find the sine square, and let me work through this problem. A square is equal to a square plus b square. Let me work this problem through. Sine square theta 1. So a square divided by a square plus b square sine square theta 1. And so the thing that I want you to observe, that you're going to take, clearly you're going to take the square root. But please note, this is a square root of the function. It could have, so your square, you're going to take a square root. So it will become a square divided by a square plus b square. And it's going to have two solutions. One is a plus solution, and you're going to have another solution which is going to be minus solution. So you are going to have, this is very important to observe, two values of theta 1. Now, the problem doesn't end here. So now you got two values of theta 1. So once you know the value of theta 1, so once theta 1 is known, we can find values of theta 2. So since I'm going to have two values of theta 1, I'm going to have from once theta 1 is known, please note I have an equation for theta 2. An equation for theta 2, I can use equation 3 or equation 4. Use equation 3 or equation 4 to find theta 2. But for each value of theta 1, you are going to have a corresponding value of theta 2. So you will have theta 2 1 and you will have theta 2 2. And you will have these two solutions, two pair of solutions. Out of that, one solution would be feasible, other solution may or may not be feasible. So what do I mean by these two solutions? So let me explain it to you what this means. So imagine that you have your robot arm, then your robot arm end effector is over here. This is the joint. So this is the end effector position. This end effector position can be achieved by, so this value or the end effector position can be same end effector position can be achieved by the other value. So this is theta 1 and theta 2. So one pair of theta 1 would represent this configuration. Other pair of theta 1, theta 2 would represent this combination. And clearly, in certain end effector positions, both these solutions are valid. In certain end effector position, only one of that solution would be valid. And in certain cases, the end effector may have some sort of constraint, a geometrical constraint, or there could be some physical constraint, or there could be some joint, or there could be some link that will not let it go in that orientation. So for an example, imagine that your workspace is restricted to the first quadrant. So clearly, the second solution that we have obtained is not possible. If your workspace is shown in the first quadrant, then clearly the second solution is not going to be valid. So everyone understood the inverse kinematics problem first part? Any question here? And let me reiterate, we just looked at case 1, wherein we formulated the inverse kinematics problem. This inverse kinematics problem, after the substitution, became problem something like this in the standard form. And in the standard form, there are two subcases. One is C is equal to 0, and other case is C is not equal to 0. So which means right hand side is 0 and right hand side is non-zero. When the right hand side is 0, this is the preferred approach, wherein what you do is you find out the values of sine, then you find the two roots, and from those two roots, you find two angles. And once you find the first angle, you will find out the second angle, and that will form a pair. Any questions here? Any question? So the next part is what happens if the left hand side is non-zero or right hand side is non-zero. So the equation that we are dealing with is a cosine theta 1 plus b sine theta 1. And now, and this is the typical case, c is not equal to 0. So how do we solve this problem? And to solve this type of problem, what I would do is I would use the half angle formula. This is the standard way of solving these types of problems. CA cosine theta 2 is represented as 1 minus tan square theta 1 by 2 divided by 1 plus tan square theta 1 by 2 plus b 2 tan theta 1 by 2 divided by 1 plus tan square theta 1 by 2. Now please note the denominator of these two equations is the same. So I can simplify this. C multiplied by 1 plus tan square theta 1 by 2 is equal to A 1 minus tan square theta 1 by 2 plus B 2 tan theta 1 by 2. Now I'm going to expand this equation completely. So when I expand this equation, it is going to become C plus C multiplied by tan square theta 1 by 2 is equal to A minus A tan square theta 1 by 2 plus 2B tan theta 1 by 2. Now please note, C is known, A is known. So what I can do is, C is known, B is known. So tan square theta is represented as U square. This guy is represented as U square, and this guy is represented as U. So please note, this is an equation of the form. So equation 5 is A U square plus PU plus C is equal to 0. And I need to write this C bar. So A bar, B bar, C bar. So this is a quadratic equation with only unknown is the U. So what I would do is I can solve this equation with the formula minus b plus minus square root of b square minus 4ac divided by 2a and find out the values of u. And I will have two values of u. So I'm going to have, since it's a quadratic equation, it will have two roots. So I'm going to have the value of u11 and u12. And I will represent u11 as tan theta 11 by 2 and tan theta 12 by 2. And from here, I can find the tan inverse, and that should give me the value of theta 1, 1 and theta 1, 2. Once I find out theta 1, 1 and theta 1, 2, just like the previous case, using equation 3 or 4, I can find theta 2, 1 and theta 2, 2. Everyone understood this? Any question here?
So when you're taking the inverse tangent, is it just the normal inverse tangent, or would it be something special because it's a half angle?
No, it would be the normal inverse tangent, because
Okay.
what you let me write this down here real quick. So what's going to happen is, so your theta 1, 1 by 2. So let me write this down. So just to be super clear, tan inverse or arctan inverse. So a tan of u 1, 1 will give me theta 1, 1 divided by 2. So this 2 goes on the other side. So theta 1, 1 becomes 2 times a tan 2 u 1, 1 comma 1. Does it make sense? And same thing happens to theta 1, 2. From 2 a tan 2 u 1, 2 comma 1. Everyone understood this? Any questions here? Okay, so that is the lesson for today. And next class, I will actually work out a problem, and I will show you how to solve this problem. So now the question is, we solve this problem for case A. How would we solve this for case B? And actually it's very simple. So basically what we got as theta 2 from all the solution procedure is nothing but theta 1 plus theta 2. So if you want to find out the values of the second angle, you just subtract the first angle from the second angle that you obtained, and then it should give you the solution. But conceptually, this problem is easier to understand. In next class, I will actually solve a three-dimensional problem, and there we will try to solve the inverse kinematics problem. So I'm going to stop here today, but if you have any questions, I would be happy to answer.